She had almost exactly the same thing last night. She had high fever, and it's unclear what it is.
Yeah, I don't know.
I mean, actually, we had COVID like 1 month ago already, so I don't know if it could be. Not really clear.
I don't know. Yes. I don't know what it could be, but I hope it goes away like yours.
Yes, we hope so.
Yeah, let me bring, collect everyone. Oyun başkanı.
Sorumlulukla genel kuralını bilmeyen şartlardan bilgin oldu.
Herkes burada yani. Başladık. Record etmek. Aynen. Yok. Orada. Durması lazım. Okay, başlatıyorum. Starting the recording.
Our second session today is going to be delivered by Eric Rousseau from Looijenga. He's going to talk about the tropical vertex. Julia Arviv was to give this talk, but she doesn't feel well. So thank you very much, Eric, to have Julia. Thanks.
Yeah, so thank you very much. So I will indeed talk about the tropical vertex. So let me start by saying that the tropical vertex is a title of a paper of Gross, Ponday, Siebert. Around 2009, and so the goal of my talk is essentially to explain what this paper is about. So the main result of this paper is some relation between two distinct topics. The first one being enumerative geometry, of curves, more precisely some version of Gromov-Witten invariance, for Looijenga pairs. So log-Calabi-Yau surfaces that we heard already a lot about in this school. So on one hand, we look at the enumerative geometry of these surfaces. We'll count curves satisfying appropriate conditions into these surfaces. And these counts will be related to something else, some combinatorial or algebraic story based on so-called scattering diagrams. And so one way to view this correspondence is to view the right-hand side, the scattering diagrams, as providing an algorithm to solve an enumerative problem, to solve a problem about counting curves in Looijenga pairs or log-Calabi-Yau surfaces. So before starting, I will just make some kind of overview without any details of where does this result fit into the more general mirror symmetry story? So this paper is roughly 10 years ago, and somehow it's set after some works and before some works. So I want to say a few words about that before coming back to something more elementary and explaining in details what's happening. So the topic really has to do with mirror symmetry. And maybe the starting point of this story is the SYZ conjecture, or maybe the SYZ picture of mirror symmetry, which predicts that you should be able to construct mirrors to Calabi-Yau varieties by looking at special Lagrangian torus aberrations and taking the dual special Lagrangian torus aberrations. But in this picture, there is something crucial coming from the existence of singular fibers. In torus aberration. Which create difficulties because for these singular fibers, you don't really know what it means to take the dual. And the prediction is that you should be able to take care of these singular fibers if you appropriately consider so-called instanton corrections. So this thing is maybe some physics-related terminology, but concretely it has to do with holomorphic disk. It should have to do with count of holomorphic disk, with boundary on Lagrangian torus fibers. So the prediction of around maybe 20 years ago was that to be able to construct the mirror, you should take into account these enumerative problems, this count of holomorphic disks with boundary on Lagrangian torus fibers of Lagrangian torus aberrations. But making sense of this count is some difficult question. So, and maybe in general, you only expect to be able to make sense of that in some appropriate limit. And so somehow, so a few years afterwards, maybe around 2002, 2003, Kontsevich-Soberman and then Gross and Siebert somehow found a way around this difficulty by remarking that under some assumptions, the ability to reconstruct a consistent mirror is somehow a strong enough condition to uniquely fix the information which would come from holomorphic disk. So concretely, they came up with a notion of scattering diagram as a purely combinatorial recipe. And then Gross and Siebert started to develop a purely combinatorial approach to mirror symmetry with appropriate toric-like assumptions on the varieties to be considered. And some other tropical vertex paper is somehow the first example where this picture of scattering diagram has been connected in a concrete way to something having to do with the enumerative geometry of holomorphic curves. So it's somehow coming back from the combinatorial recipe, going around the difficulty and coming back to the enumerative geometry of holomorphic curves. So it is in this sense that this paper is significant, that it makes this contact between the kind of heuristic of enumerative geometry of curves and the concrete combinatorial recipe of scattering diagrams. And then afterwards, his work was used in an essential way for the growth I can kill. Mirror construction for log Calabi-Yau surfaces. And since then, the picture has been almost fully generalized. I know as a theory of logarithmic and punctured Gromov-Witten invariants, there is some kind of entirely algebra geometric version of this instant hand corrections picture, which give rise to a kind of complete, almost complete general algebra geometric mirror construction. And I guess we'll hear much more about that from Groth and Siebert in the conference next week. And in particular, this story about the tropical vertex, which is about a concrete algorithm to solve some enumerative problem or about curves in surfaces, has been generalized recently in a paper called the higher dimensional tropical vertex. By Agus and Groth, which consider curves in higher dimensional log Calabi-Yau varieties admitting a toric model. Okay, so this thing was just to give some perspective of where this paper is sitting. So from now on, I will come back at the beginning of the story. So what I will talk about in this talk is first talk about the enumerative problem. We'll be talking about curves in Looijenga pairs. Then I will talk about scattering diagrams. Then the main result, which is a correspondence between 1 and 2. And if I have some time at the end, I might say a few words about the proof. Okay, so let me start by the enumerative problem. So what is our setup? Our setup is a Looijenga pair, XD. So as in many of the previous talk, X is a smooth projective surface. Over complex numbers, and D is a number crossing anti-canonical divisor. So Kx plus D equal to 0, and we assume that D is singular. So D has at least one node. So under this assumption, we saw in the previous talk that such a pair admits a toric model. So in other words, typical example of such a pair are given by toric pairs. For example, here I draw a picture of toric P2. So I drew 3 lines in P2 forming the toric boundary of P2. So it's P2 with its toric boundary. It's an example of such a pair. Or other example can be obtained by starting with such toric pairs and then blowing up points living on the smooth part of the boundary. For example, I could blow up this point. And when I do this blow up operation, there is an exception divisor which is created. And so my new surface is this blown up surface, and my new divisor is a strict transform of the toric divisor. So it is still the red triangle on this picture. And we can consider a more complicated example I guess, for example, in Travis' talk yesterday, he was considering a cubic surface, which was obtained by starting with P2, and then by blowing up 2 points on each of the 3 boundary lines. So in total, we get a surface, which is P2 blow up in 6 points, which is isomorphic to a cubic surface in P3, and with a anti-canonical boundary consisting of 3 lines. Okay, so the other kind of surfaces that we are considering. And now we want to consider curves in such pairs of a particular type. So actually the curve we'll care about will be so-called A1 curves. And in first approximations, they are rational curves in X, meeting D at a single point. So concretely, the simple example of such a thing will be a map F from P1, the complex projective line, with one map point that I can decide to call the point infinity on P1. So if you want, my domain curve is also a pair, just a P1 with one mark point, and I want this pair to map to the Looijenga pair XD. And I want the preimage of the divisor to consist theoretically only of the point infinity. So the first remark to make is that such a curves do not exist if XD is toric. So remark, if XD is toric, A1 curves do not exist. So for example, let's look at the case of P2. With toric boundary. And so what would be a A1 curve? It would be a curve in P2, which by definition touches this triangle in only one point. It is the definition of A1 curve. But a curve in P2 has some degree. So this curve has some degree D. And if this curve is not constant, we don't care about constant curve, it has some degree D, at least 1. But then a curve of degree D needs to intersect each of the 3 lines in at least D points counted with multiplicities. So another way to say it is that each side of the triangle is ample, is actually very ample. And so any curve needs to intersect them. So indeed, such picture in P2 is not possible. In P2, the only picture that you can have is, for example, if you consider a line in P2, then this line will, maybe I drew a line like that, the line will intersect the boundary in 3 different points. It's not possible to find a curve intersecting the triangle in a single point. But if your Looijenga pair is not toric, then typically there exist A1 curves. An example of A1 curves are actually given by exceptional curves. if you realize your surface as a blob of some toric surface, for example, if I start with P2 and if I blow up one point of the boundary, I have an exceptional divisor. Let me call it E. Then actually, this exceptional curve is an example of a one curve. Why? Because an exceptional divisor, when you blow up one point, is isomorphic to a P1. So definitely it is a rational curve. And on the other hand, it intersects the boundary in a single point, which is exactly the strict transform of the point you blow up. Okay, so in general, we have some A1 curve, which are the exceptional curves. But more generally, we can have more A1 curves. So we can have there are more A1 curves. Actually, in this picture that I've drawn of P2 blown up in one point, there is one more A1 curve. You can start, if you start with P2, and in P2 you can look at the line passing through the point we blow up here, and this corner of the triangle. Okay, so in P2 there is a unique line passing through these 2 points. And now you can look at the strict transform of this line inside the blob geometry. You will get something which looks like that. And this red thing will again be a one curve. So it will be a P1 because it is a strict transform of a line in P2. And it is touching the boundary in a single point, where here this point is a corner, this corner of the triangle. And in more complicated geometries, you can produce even more A1 curves. So let me make a precise definition, or almost precise definition, of the kind of counts that we want to make. So we want to count A1 curves. So to be able to count, we need to fix discrete data. So the first thing we need to fix is a homology class of this curve inside the surface. So we fix beta in H2 of the surface. And we also want our curve to touch the boundary in a single point. And so necessarily at this point, the curve will have some tangency condition, will satisfy some non-trivial tangency condition with the boundary. And so we can encode this data, this contact order, denoted by M. And conceptually, you can think about it as some integral point inside the tropicalization of U, where U is a complement of D inside X. So here I'm using a notation which I introduced yesterday, at least in Travis' talk, that if you have a Looijenga pair, you can talk about its tropicalization, which is simply the data for each corner of the divisor. You have some corresponding two-dimensional cone, standard two-dimensional cone. And then these cones are glued together according to the intersection pattern of the divisors. And the point is that you can think about an integral point inside this picture. So for example, the point M here. So M is an integral point. It means it is of the form A, comma B, where A and B are coordinates for points inside this cone, this two-dimensional standard cone. So it means that, okay, I don't know if my x-axis is like that, it means that here I have coordinate A and here I have coordinate B. And how do I want to think about this point M? I want to think about it as prescribing contact orders for curves in X along D. So what does it mean? Here, this point M is inside this cone, which is drawn here, which by definition corresponds to this corner of the triangle. And if I fix M equal AB, it means that I will look for A1 curves touching D at this particular point, this particular corner. And I want the contact order of this curve with this divisor here to be equal to B. And I want the contact order along with the other divisor to be equal to A. So I want to think about AB as prescribing contact orders for a curve along the various components of the divisor. So for every such beta and M, there will be a count and beta M, which will be a count of A1 curves in X of class beta with contact order M along D. So maybe just I give an example I've already given, but using this notation. If I was looking at P2 and then blowing up one point, creating an exceptional divisor E, then the tropicalization so there is one cone for each of the corner. And this exceptional divisor E is a contribution to count of A1 curves of class beta equal to the class of the exceptional divisor. And the contact order M is a point here on the ray which is dual to the divisor or to which the exceptional divisor is touching, and the integral point at integral distance 1 from the origin. And why is it 1? It's because this exceptional divisor intersects transversely the boundary. So there is no, it's really transverse intersection, so the intersection number is 1, which corresponds to this choice of contact order. And actually, you can check that for this geometry, if you are looking for A1 curve of class beta equals the exceptional divisor, with this contact order equal to 1, actually there is a single A1 curve, which is the exceptional divisor itself. And so in this case, this count is simply equal to 1. So in general, when I talk here about counts, as usual in normative geometry, one needs to be careful about what one really means by counting things. So precisely, and beta m is defined as being a log Gromov-Witten invariant of the pair XD. So the point being that if you just have an ordinary variety X, not a pair, and if you are interested in counting curve in X satisfying various conditions, and if you want to do that in a way which produces deformation invariant answers, then one way to do that is to do Gromov-Witten theory, to really count of stable maps, and then there is a whole machinery producing compact moduli spaces from which you can extract numbers, so-called Gromov-Witten invariants. And in the case where you count curve inside the variety X, where you also impose tangency conditions along a normal crossing divisor D, which is a situation in which we are here, there is a generalization of Gromov-Witten theory called logarithmic Gromov-Witten theory, which has been developed by Abramovich-Chen. And Gross and Siebel. So yeah, we just keep it at some kind of technical black box. Just a remark for why you need this kind of more elaborate definition and why some of the most naive definition is not necessarily the good one, is that as it happens in ordinary Gromov-Witten theory or in ordinary curve counting problem, you can have so-called multi-cover contributions. For example, if I still go back to my example of P2 blow up in one point, but now I do not consider the class of the exception divisor, but I consider the class which is a positive multiple of the exceptional divisor. So I consider class K times the exceptional divisor. And so correspondingly in the tropicalization, I'm looking to the contact order, which is at distance K from the origin. So if I look at this problem, and if I'm looking at maps from P1 to X of class K times E. But one way, and in fact the unique way to produce such a map is to construct a map from P1 to E, which is generically K to 1, and then compose with an embedding of E inside X. So all these curves will be generically covers of E. And in fact, there are not finitely many such covers in general. There is a moduli space of such covers. And so you need to do some so-called virtual work to extract numbers. Another way to say it is that when I'm talking about count of A1 curves, for that even to make sense, I need to know that there are only finitely many A1 curves so that I can count them. And you can argue that somehow the expected dimension or the virtual dimension for the moduli space of A1 curves is indeed 0. So in the ideal situation, you expect to have finitely many A1 curves. And you see that in the nice cases, it is indeed the case for the exceptional divisor. this exception divisor is a rigid curve inside my surface. It does not move. So indeed, this A1 curve is something isolated, and I can just count it, and I just get the answer 1. But in more complicated situation, because of this covers contribution, the true dimension of the moduli space is bigger than the expected dimension. And then you need to do some work to extract numbers out of it. And actually, in this case, if you really consider this concrete example, this particular exceptional curve and the class K times the class of the exception divisor, and if you take M to be this point, then you can compute the number after some work. And actually, you find that this number is -1 to the K minus 1 divided by K squared. In particular, it is a rational number, not an integer in general. So when I say that there are counts of A1 curves, in general, this thing needs to be taken with a grain of salt. It's really a virtual count in complete generalities, and complete generalities are really rational numbers defined through some Gromov-Witten machinery. Okay, so before switching to scattering diagrams, let me just make some kind of symplectic remark for why you might care about A1 curves. Is there a question? I see someone.
Can you hear me? Oh, can you hear me now?
Yes, I can hear you now, yes.
Yeah, so I just got confused about your tropical
yes.
pictures. So what you drew looks to me like a tropical line, but we are dealing with surface. So I don't know how to read your picture.
I'm sorry, it's because this picture really includes these two-dimensional cones.
Oh, and this is a planar picture, or I should think of them as like three corners in three walls in space, or what?
So, okay, so there is 2 levels at which you can think about this picture. The first level is just as an abstract cone complex, just 3 cones glued together. And at this level, it does not matter if it is in a plane or in space.
Mm-hmm.
But there is a more refined level, which I guess was discussed in Travis' talk yesterday. You can put a natural integral affine structure on the complement of the origin on this picture. By some recipe determined by the self-intersection number of the various divisor component of the surface. And in such a case, this picture, as the integral affine manifold with singularity, is no longer embedded inside the plane with this standard integral affine structure. But it's some kind of more abstract integral affine manifold with singularity.
Thank you very much.
Yeah, thank you for the question. So just without any details, because I don't think it's fully understood how to make this thing precise. The symplectic picture is that this complement x minus d of our surface is a non-compact Calabi-Yau. And it admits a Lagrangian torus aberration with some number of singular fibers. And some of the symplectic point of view on the XYZ picture tell us that mirror symmetry should involve holomorphic disk in this geometry with boundary on these Lagrangian torus fibers. So maybe here I draw something which is supposed to be a picture of a disk. So the disk has a boundary here, wrapping a cycle on this particular torus fiber. So this thing is what maybe you should consider from the symplectic point of view. Whereas here we are adopting some algebra geometric point of view by considering A1 curves. So in our algebra geometric perspective, you already consider the compact geometry X, where you add the divisor D at infinity, So maybe on this picture, I draw something like D. Maybe D is somewhere at infinity, something like that, very roughly. And it's kind of made of P1, so it's kind of made of things which have circle like that. And the naive picture of what the relation between this holomorphic disk and the A1 curve is that you can imagine that if this holomorphic disk ends on some Lagrangian torus fiber, which is somehow very close to infinity, then you might hope to be able to close it in a canonical way by gluing a disk on the other side, touching infinity, the divisor at infinity in one point, to produce a closed curve, a closed P1. So the full thing, sorry. So the full thing here will be a closed P1 touching the boundary in a single point. So it will be an example of A1 curves. So the heuristic is that algebraic geometrically it's much easier to work with closed curve, which makes sense in algebraic geometry. You count this A1 curve going at infinity. But heuristically, for many purposes, you want to think about it as cutting it into two and think about it as having to do with holomorphic disk. Okay, so now let me come to scattering diagrams. So the most scattering diagram will be the answer for how do we compute all these counts of A1 curves, all these numbers, how do we compute them? And the basic idea is that we know some example of A1 curves, we know the exceptional curves, but we know that there are many others. And the idea of the scattering diagram story, it will be somehow a way to reconstruct arbitrary A1 curves, starting from the initial data of the very simple A1 curves given by exceptional curves. Okay, but before coming there, I need a little bit of terminology and notations for what scattering diagrams are about. So there are various settings to talk about scattering diagrams, and I will talk about the simplest story. And in this simplest story related to Looijenga pairs in dimension 2, the scattering diagrams will live in R2. So it's an ordinary real plane. And the scattering diagram will be, by definition, will be a collection of so-called walls, which in complete generality will be codimension 1 loci, but here because we're in dimension 2, they will simply be codimension 1, so dimension 1. And concretely, there will be either lines or rays. So what do I mean by that? By line, I mean any line in R2 of rational slope. So line, so any line of rational slope. And by rays, I mean any half line of rational slope, meaning it just starts at any possible point in the real plane, and then it goes in some rational direction. So in particular, because of this assumption on rational slope, it means that I can find some direction vector. So let me denote by M0 in Z squared, some direction vector, and I can pick it to be primitive, meaning with coordinates which are co-prime. and I take it in this direction, going from the starting point in the direction of the half line, when you have a half line. And actually, when you have a line, I also take the orientation as being part of the data. So actually, it is an oriented line. And so I also have a direction vector, primitive direction vector, M0. So actually, this thing is the first half of the data, just collection of geometric loci inside the plane. It's not much data at this point. So the second piece of data is that each of these walls, so as a line arrays, so for example, if I have an array like that, of direction M0, then this array is decorated by a function. F, which is a power series in some monomial z to the power M0. So here I'm really thinking of M0, I'm using some kind of multi-index notation. So z to the M0 is a monomial corresponding to the vectors M0. So if in coordinates, it's really function of two variables. And then I tensor, and I take a completed tensor product by some ring, some kind of ring of coefficients, which is just some ring of power series, means some variable T1 to Tk for some numbers of a formal variable. So what do I mean exactly by this notation? I really mean that this ring of power series, let me call it R to simplify the notation. It's really a local ring. It has a maximal ideal made of all power series, like with zero constant term. And then this full thing by definition is some kind of limit of this polynomial ring tensor by the ring R divided by the maximal ideal to the power K. So concretely, what is this thing? F is some kind of power series. It has Z variables and T variables. And this complicated looking notation just guarantees that at finite orders in T variables, everything is finite. And the relation between this function and the ray is that the power of Z has to be a multiple of the direction of the ray. Okay, so this thing is a definition of a scattering diagram, so maybe it looks a bit strange. It's like I have some maybe one ray like that, some line like that, another line like that. And attached to this line is some function, maybe f1, satisfying this condition of this form. And attached to this line is another function, f2. Okay, so at this point, the scattering diagram is just a collection of lines or rays decorated by power series. So the important notion, which will make the story non-trivial, is the notion of consistent scattering diagram, which will be a very non-trivial condition on this collection of lines decorated by functions. So let me explain what it is. So to define it, one is first to define a notion of wall crossing when you cross a line or array. So if you have such a line or array, which is part of your scattering diagram, and if it is decorated by a function f, and if you have something different, some oriented paths in the plane, which happen to cross this line or this array, then you can attach to this intersection point the so-called wall crossing automorphism which maps a general monomial of the form z to the m, where m is an arbitrary element in z squared, so arbitrary Laurent monomial in two variables, and you map it to z to the m times the function attached to the ray to the power, the pairing between n and m, where n is the primitive normal vector to the ray which is, let's say, which is negative before the intersection. So what do I mean by that? As a ray, it's something, it's a locus of codimension 1. So it has a normal vector which really live in the dual space of this lattice z squared. And because it's something rational, it has a primitive integral normal vector. So, if I think that I have some Euclidean scalar product, I really think to my normal vector as being something like that, but intrinsically it really lives in the dual space. And I have some choice if I orient it in one way or the other way, and I fix the orientation by asking that it has negative evaluation of the part of the path entering and positive on the part of the wall going out. And then what is here is a natural pairing between the lattice z squared and its dual lattice. Okay, so you can think about this function attached to the rays at defining wall crossing transformation. They tell you how to transform monomial z to the m when you cross along a path across such a line or such a ray. And it's given by this explicit formula. And now you say that your scattering diagram is consistent. So I have my scattering diagram, correction of lines, decorated by functions. If for any choice of closed loop inside R2, if you do the product of wall crossing automorphism, that you find each time you cross the ray of the scattering when you move along this path. So here you have some wall crossing automorphism at this point, then you continue. Here you have a new wall crossing automorphism. So you take the product, meaning the composition of these two wall crossing automorphism, and you continue. So here you have a new one, here you have a new one, and at some point you come back to your starting point. As a non-trivial condition that this product or composition of wall crossing automorphism has to be the identity. Meaning if you start with any monomial z to the m for any m in z squared, then you should go back to z to the m at the end of the day. And the claim is that this condition to be consistent is a very strong condition. So to be consistent, consistency is a strong condition. For example, here is a concrete scattering diagram. I take one horizontal line, and on it I put the function 1 plus t1 times x. well, here by x I really mean z to the power 1, 0, which is the direction of this line. So this thing is some allowed function to be attached to the ray. And then we consider this different line where I attach the function 1 plus t2 times y. Then the claim is that this scattering diagram is not consistent. So this thing. So it's an exercise that I don't have time to do it. So you really apply this row crossing formula to a loop going like that. So you need to apply it 4 times. And you will see that when you come back to your starting point, you do not go back to the identity. But the non-trivial fact, I mean, the fact is that if you have a scattering diagram which is not consistent, you can make it consistent. So let me say the initial scattering diagram made of lines, like on this picture, can be uniquely completed into a consistent scattering diagram by adding only rays. So on this example, I have these 2 lines decorated by this function. And the claim is that this scattering diagram is not consistent. But what this fact is saying is that there is a way to modify this picture to add a ray somewhere on this picture decorated by some uniquely determined function so that the new picture is consistent. And the answer is to add this middle ray, so of direction 1, 1, decorated with a function 1 plus t1, t2, xy. And the claim is that this new scattering diagram is consistent. And it's again some explicit exercise to check that it is the case. So now I need to come back to the main point. I need to explain what this scattering diagram story, what does it have to do with accounting A1 curves.
So the functions can be essentially anything, right? There's nothing.
Yeah, so maybe I forgot some small, okay, maybe some technical condition for the wall crossing automorphism to make sense. I need f to be equal to 1 modulo the maximal ideal. My function, as on this example, they start with like modulo the ti's that I go to 1. Because more generally, there might be like power series in the t variables. And so in order for like product of this power series to make sense, I need to have a constant term 1. But yeah, apart from this kind of convergence condition, at this point, they're essentially arbitrary things, yes. So, but in 1 minute, I will describe a concrete scattering diagram which will first be given in terms of lines decorated by concrete explicit function as simple as 1 plus t1x. And then we will care about the function which are produced by the consistency condition. And these functions are uniquely determined by the consistency condition, but they can be very complicated. Okay, so let me come back to geometry to finish. So let's say I start with a toric surface, again my P2, and let's say I cook up a non-trivial Looijenga pair by blowing up 2 points. Then I can cook up a scattering diagram out of this data. I include a line. So from that, you cook up a scattering diagram. How do you do that? You include a line for each of the points you blow up. And you take this line to be in the direction of the ray in the fan of the toric variety of the toric surface on which we are blowing up this point. So here I'm blowing up this point on this side of P2, which in the fan of P2, if I draw a dual fan, in some horizontal direction, so I draw some horizontal line. And similarly, I'm blowing up a point on the other side, which corresponds to a vertical ray in the fan of P2. So I also draw a vertical line. And I decorate this initial one by something very simple, 1 plus T1 times essentially Z to the power of the direction, the primitive direction of this line. So in this case, the primitive direction is just 1, 0, so it's just X. And here I decorate it by 1 plus T2, 1. And I introduce a variable Ti for each ray. Like for the first ray, I just put some T1. For the second ray, I just put some T2. If I have more rays, if I blow more points, I have more rays, I have more Ti variables. Okay, so I get this very simple scattering diagram, which is exactly the form I was talking about previously. Just the combinatorics of which point I blow up to construct my Looijenga pair. I can use it to just write down these very simple lines in R2 decorated by this very simple function. Now the non-trivial recipe is to write down the corresponding consistent scattering diagram. And the claim is that there is an algorithmic way to do that. So this fact says it's telling you there is a unique way to do that. Actually, there is an algorithmic way to do that. And as I explained before, in this example, you need to add this array with function 1 plus T1, T2, X1. And so now what does it have to do with a one curve? So essentially the theorem, the main theorem of the tropical vertex paper of Groth-Pondai-Zibert is that these functions f attached to the rays of the consistent scattering diagram are generating series of the counts of A1 curves. So because I'm already over time, I will not write down the precise formula. I will just finish by an example. So in this example, to get a consistent scattering diagram, I had to add this red ray in this 1-1 direction. And the theorem tells you that the existence of this ray has to do with the existence of particular A1 curve in this particular log-Calabi-Yau Looijenga pair. And the dictionary, the direction of the ray, has to do with the contact order. So because this ray has direction 1-1, which is a part of the fan of P2, which is dual to the side of the triangle, it means that this ray has to do with a one curve touching. So by definition, a one curve touches the boundary in a single point. And because this ray corresponds to this side of the triangle, my A1 curve needs to touch at a single point. And finally, the information about the T1 and T2 variable, I could explain, but it will take a little time, actually encode the information about the curve class of this curve. And you can find that indeed there is in this geometry a one curve looking like that, which in the original P2, if I just start with P2, there is a line passing through the 2 points that we blow up. Or maybe it will not really look like a line because I'm drawing some strange picture. But if there is a line in P2 passing through these 2 points, and this line intersects the third side of the triangle in a unique point. And now if I take the strict transform of this line, it will no longer meet the 2 sides because now it will meet the exceptional divisor there and there, but it will still meet the third side in a single point. And so you see in this picture that you have A1 curve in green, which are simply the exceptional divisor, which in the scattering diagram picture are some kind of initial lines, which are very easy to write down. But then there are more complicated A1 curves, such as this black one, which is somehow produced in some way by the interaction of the 2 exceptional divisors. And in the scattering diagram picture, they correspond to the rays that you need to add to make the scattering diagram picture consistent. Okay, so sorry for rushing a bit at the end, but the upshot is that on the one side, you have this combinatorial recipe, this scattering diagram, that you can just implement on a computer, you can just compute things. And this picture on the right computes something on the left, which is this iterative problem counting these M1 curves. And I will stop there. Thank you.
Thanks, Thierry. Any questions here?
Yeah, I'm sorry, can you repeat? Okay.
Just your
Can you point out the name of the dog here, like tropical vertex?
So I could not hear. Could someone maybe repeat the question? Or
I can repeat it. So can you tell him where the name tropical vertex appears in this picture? What is the tropical vertex he's asking?
you mean the name? Where does the name come from, maybe? Or
Yes. Like,
yeah. So
where is the vertex?
yeah, very good. So I think the vertex is this thing. Is a place where the scattering is happening around the origin. So it's a vertex because it's a place. So in general, you have these initial lines. Yes, these initial lines are always supported on rays of the fan. So they always meet at the origin. And so some of the non-trivial condition for the scattering diagram to be consistent. So in general, a phrase for a general scattering diagram, you need to check every possible closed loops. But here, if all the initial rays just go through the origin, the only interesting loop to check is a very small loop going around the origin. And then you need to add rays, and all these rays are coming out of the origin. So somehow, in some kind of figurative way, you have initial lines, and they meet at the origin. And at the origin, they scatter, which is the origin of the name scattering, because they produce new rays. And the place where they all scatter, the origin is a vertex. And maybe I should say one more comment. Why is it tropical? So the claim is that this picture should be viewed as some kind of tropical picture. And okay, so to make that precise require a little bit of work, but actually the proof of the theorem relies on some degeneration argument. And the count of A1 curves is reduced to some count of tropical curves in R2 in the plane. And so this scattering diagram picture, maybe already there, it's possible to see that it looks a bit like tropical thing. For example, just this configuration of here looks like a tropical line. And in fact, it's not a coincidence that in some appropriate degeneration limit, you can degenerate this non-toric geometry to some toric geometry, and then this black line becomes some honest line in some honest toric variety, which after tropicalization becomes this tropical line. So actually, one way to think about this correspondence between A1 curves in Looijenga pairs and scattering diagrams is some kind of generalization to some non-toric setting of some kind of tropical correspondence theorem. Like if you care about counting curves in toric varieties, there are ways to do that, going back to Mikhalkin or Nishino-Zibert, and which involve drawing tropical curves in R2. And here our geometry is no longer toric because it has been obtained from some toric geometry by making this non-toric blob. And but still we can compute in some kind of tropical way the answer, and this thing is a scattering diagram.
I wanted to also just, is there any way to show us the fourth and fifth curves as well? Like, you know how
you mean
the vortex, the upper vortex to the
yes. Yeah, so in this picture also some.
But I don't understand the tangency.
Yes, so okay, so here, if in black this tropical curve, I really think about it at the very beginning, it's a fan of P2. And so for the part of the scattering diagram corresponding to one of these three black things, it is relatively easy in the sense that if the ray coincides with the part of the fan, a ray of the fan, it means it corresponds to one toric boundary component, and it means that this curve intersects the boundary along this toric boundary component. So for example, if I take this horizontal line here, its function corresponds to this exceptional curve meeting this side on one point. Similarly here, this thing corresponds to this exceptional divisor meeting this thing in one point. And this black thing corresponds to this curve meeting this thing in one point. I guess maybe your true question is about the last one.
Yeah, I'm asking about the other two.
Yeah, so this horizontal one here that now I'm putting in blue. So now this thing is no longer part of the fan of P2, right? So the correct way to interpret it is that saying that this ray is going inside the cone in the fan of P2, which is dual to one of the corner of the triangle. Right? This whole cone is dual to this corner. So it will mean that this ray corresponds to some A1 curve, which is touching the boundary at one of these points. So it is upon what I'm talking about A1 curves, a curve meeting the boundary divisor in one point. But this point could be a smooth point, or it could be a singular point. It could be a corner of the divisor. So actually, in this example, it will go into the corner, and the fact that it is a specific line, which is somehow the sum of the two rays generating the cone, means that the contact order with the two sides is equal to 1. So actually, I'm looking to a curve which is going to the corner and touching one side of the triangle with contact order 1 and the other with contact order 1.
Yes.
And in fact, I can tell you exactly what this curve is. It is simply the strict transform of a line in P2 passing through this corner, and the point will blow up there.
Yes, I got confused with which coordinates we're using. We're using the cone's coordinates, not the coordinates on the plane. So we need to, like the blue thing.
Yes, exactly. Yes, sorry. Yes, so when looking at contact orders.
No, you said this. You said this exactly correctly. I just forgot.
So indeed, it is like that. Yes. Yeah. So in this picture, you can really see the 5 curves. There is one, and the last one is the other one. Something like that, which is the other line going to this point, which is a strict transform of the line passing through this point.
Another question. Also, oh yeah, sure. So we sort of saw in previous talks how you get from some collection of exceptional curves to all the other exceptional curves using this mutation. So that's sort of clearly part of this picture, in that it produces exceptional A1 curves. But like, how do you get non-exceptional A1 curves just from the initial exceptional collections? Or like maybe, yeah, like what's an example where like a non-exceptional A1 curve arises?
Yes. So you mean?
Yeah.
Yeah. So do you mean that in this example, like all the curves, somehow they're all exceptional, right? Is it what you mean?
Yeah.
I mean, but even that is not okay. Is it?
Is it true? Why is the last?
Yeah, because the thing going in the corner in some ways are not really exceptional in the.
Well, let's say potentially exceptional on some.
Yes. Oh, okay. Maybe I can just give a clearer example where there is clearly something which is not exceptional. Let me just give the example of the cubic surface. So P2, and I blow up 2 points here, 2 points here, 2 points here. And so an example of interesting A1 curves, which are actually much more interesting than all the ones I've been talking about until now, is to look in P2 to connects passing through 4 of the points you blow up. So here is a general connex passing through 4 points. So this thing is just a connex in P2. And there is a 1 parameter family of it, right? If you fix 5 points in generic position, there is a unique conic. If you only fix 4 points, you get a pencil, a 1 parameter family of conics. And a generic conic in this family will meet this line in 2 points. But there are particular elements inside this family where these 2 points actually come together, where the conic become actually tangent to this line. And now if you consider the strict transform of this curve in the blow-up geometry, it will be an example of A1 curve, because it will no longer touch here, because here we blow up, but it will touch here in a single point, and here it will be really tangent to the line.
Sure, that example makes sense. I guess I was asking though, like, somehow that curve, you can discover the existence of that curve from only the data of your initial scattering diagram, which is just your original 6 blow-ups.
Yeah, so the claim.
So like, how can you, I don't know, is there a geometric way to see that this red curve exists from, well, I don't know. We could talk about it later.
Yeah, I mean, maybe just a single thing I can say that, I mean, in the symplectic heuristic, if you think about this kind of holomorphic disk moving in some torus vibration, some other scattering diagram will tell you how to glue this disk together to cook up more complicated curves. So in this kind of picture, so definitely, like if you compute the scattering diagram, I mean, you can really compute it like with some kind of 6 initial thing, and you run the algorithm, and the algorithm will tell you there is something corresponding to this curve. But if you think to this thing as being some kind of tropical picture, you should think to see the red thing as, you should think to each of these exceptional things as producing some kind of initial small holomorphic curve, maybe like that. And then somehow the curve we really care about is obtained somehow by merging together these curves, but somehow the non-trivial thing is how exactly does it happen? And some of the non-trivial part of the theorem is that the scattering diagram is a correct answer for how does it happen. And maybe like the algebra geometric proof, I mean, maybe if you go through the proof, you can get some kind of explanation. You do some kind of degeneration, and then you might see at the end your curve will break into pieces, and maybe you can understand more concretely what's happening.
I have a question. Could you explain again how to get the function from the non-toric block picture? And how does one, how did you get that 1 plus T1x and 1 plus T2y and stuff like that? For this complicated picture, like what would I be drawing?
So sorry, I could not yet hear. Maybe just could someone repeat?
No, I was just asking, like, could you explain again, like, how to get the functions from the picture?
Yeah, so from yeah, so actually there is something. So you mean the initial functions, for example, or the final functions?
Both actually.
Yes. So.
But at some point, someone has to read the paper.
No, but somehow it is hidden that in the fact that I did not state the theorem fully, and actually there is something very non-trivial happening somewhere. So like the first approximation of the answer, which is a bit wrong, is to say that it's 1 times T1 times X. So here there is a coefficient 1. And it's related to the fact that there is a single exceptional curve. So in general, your power series will have like x to the power a, y to the power b, and maybe some powers of t1 power something, t2 to the power something. And as I was trying to explain before, the powers of x and y, maybe in correct cone coordinates, are related to the contact orders of the curve you are looking at. So it's related to what I was noting before by M. And the powers of T's have to do with a curve class. So it has to do with beta. There is some recipe out from the T variables to cook up a curve class beta. And then the coefficient in front of that roughly should be related to the count of A1 curve and beta M. So here, because there is a coefficient 1, it's related to the fact there is a single curve. And similarly, here the coefficient is 1, because again, here there is a single curve. Whereas, for example, in the example of this cubic surface, actually this particular...
Yeah, but you have to, you have to exponentiate it.
Yeah, that's what, so okay, I just wanted to arrive there. So here, I say it is approximated true, it's not correct. Yeah, so there is a fully correct formula. The fully correct formula is to say that function f is some exponential sum over k greater or equal than 1, k times n beta k times m0. And let me write something schematic like t to the beta k m0. So if m0 is a primitive direction of the ray,
even this, you have to take like some Poisson bracket with the, don't you think, something like that?
So I think here I've written it in the correct way because I put a factor k here.
Oh yes. Sorry. Yes.
And so indeed you can check that at some point I talk about this multiple cover story where you just have exceptional divisor contributing 1, but then I claim that if you look to multiple of it, it will contribute something a bit weird, like -1 to the k minus 1 over k squared. And so if you just plug this number into this formula, you will get something like k times -1 k minus 1 over k squared, t to the beta z to the k. And this k squared produce some 1 over k. So actually this thing is some kind of power series expansion of some logarithm. And so when you take exponential of the logarithm, you exactly recover 1 plus t to the z to the power m0. So indeed, it's perfectly correct. The precise formula is a bit complicated. It involves this exponential and this k factor. and it has to do with this multiple cover phenomenon. And in particular, this initial function 1 plus t1x, they are somehow deceptively simple somehow. They do not just come from the fact that there is a single curve, but they come from the fact that there is a single curve, and all these multiple cover has a very specific structure. And when you resum all of them, there is some kind of big constellation between the x and the log. And at the end, it just produces 1 plus t times z to the power of something.
Thank you.
Any question in the Zoom room? Here. Okay, let's thank Eric again.
Thank you.
Your time. 2:55. Okay, let's meet 10 past. Okay.